Okay, so we're going to start the slide set is my chapter 8 from New River. In your book, it'll be chapter 8 and section 9.1 through 9.3. Okay, so that's the way it's organized in brown. So there's so much information to be covered concerning the nature of the chemical bond and the theories that have developed over the years that we're dividing it into two exam materials.
Two exams?
Huh?
You're going to 2 exams on the bonding?
Yes.
Okay. So that'll be our last 2 tests?
Yes.
Oh, goodness gracious.
Yeah, and the last test will be during the final exam week.
Around December.
Yeah, December something.
I'll give it on December 2nd. I don't even know what December 2nd. Is December 2nd on a Friday?
No.
Okay.
December 8th.
Yeah.
December 8th will be when we meet for that. So all this discussion of bonding, we're going to cover it in more or less historical order because it developed slowly with a couple of big jumps. But the first material we're going to cover gives us some understanding about the chemical bond, but it's not complete. I mean, it's not entirely accurate. But we have to start there because some of the concepts are useful in making predictions about the chemical bond. So let's get started. All right. First question we're presented with now and historically speaking is, what do we mean by a chemical bond? That's one of the questions we need to answer. And then we want to know, why do atoms bond with each other to form compounds? I mean, why aren't they just happy by themselves? Like, no, as it turns out, huh?
Because the electrons have to be balanced, right? So
Yeah. You're on the way. Right, there are very few elements that are not bonded with something in nature. Of course, the noble gases, right? They don't bond with anybody unless you force them. And there are some noble elements that don't bond, gold in particular. But all the other elements in nature, you're going to find them as in compounds. In fact, most of the metals in the Earth's crust are some kind of oxide. Then we want to know not just why they bond, but how what's the mechanism? How do they actually fit together in these molecular forms? So we start with Dalton's atomic theory, right? We start there because unless we appreciate the fact that all the elements are made up of atoms that are unique to each element, then I mean, there's no place to go from there. So we owe all of that to Dalton and his atomic theory. Right, there's really no simple answer, but what we can do is start off with as simple as possible a concept of the chemical bond. And that has to do with the forces. What is the force that holds atoms together? That's what we call a chemical bond. So that they can function as a unit. All right. One thing we do know is that if we think of it in terms of energy, the energy of the individual, say we just have 2 atoms, like, I don't know, sodium and chlorine. As if it was chlorine, it'd be like that. But the energy that's associated with this situation, right? The energy of the reactants versus the energy of the product, right? So, well, let me balance it. There you go. How about that? The energy of the product, let's see, let's do it like this. Products and the energy of the reactants. When you look at it this way, what we notice is that the energy of the products are always less than the energy of the reactants. So the reaction tends toward lower energy state. Now I can think of some reactions where that's not true, but on a local scale, this is an overall reaction. Somewhere in the middle, we stop the reaction in the middle, they might be at a higher energy level, but eventually they get down to this level. And perfect example of that is nitroglycerin. Right? When you take the glycerol molecule and you have nitric acid and you need some sulfuric acid in there too, mix them together, you end up with nitroglycerin. And everybody knows that it's very high energy compound. But the energy of the reactants was lower than the product, right? But if we let it go to completion, right, it drops way down. So it's an intermediate step. But in general, and in fact, when we're looking at individual atoms, and if we can break it down to single bonds, where you're bonding this atom with that atom, and we're not adding any complications to it, then this pretty well holds. The energy of the reactants is greater than the energy of the products. That means stability. When we look, we're going to take this particular example is an ionic bond. Ionic bonds are the easiest ones to understand because they are purely electrostatic. I'm sorry?
That's not what I thought you were gonna say. They're the easiest. I just remember ionic because it's ironic, the opposite.
Yeah.
That's what I thought you were gonna say.
Oh, no. That's a good one, though. We can actually calculate the force that's holding these two ions together. And all we need to do is use Coulomb's law. There's Coulomb's law in a form that we can use for our problem solution. Coulomb's law comes in various forms. But in general, the energy of attraction for these two oppositely charged ions is some kind of constant, and there's the constant that we're using, 2.31 times 10 to the minus 19 joule meters. And then it will always have one charge and the other charge and divide by the distance between them. Okay? And since the constant has nanometers in it, this is going to be in nanometers because they have to cancel, and the energy is in units of joules. So that works out. This can be either two pluses or two minuses. In our case, it's a plus and a minus.
You're really missing the party. I'm not sure what it is.
It's Governance Day.
Governance?
Yeah, Governance Day.
Right.
It's where all the committees come together and meet, and the faculty senate meets. Everybody does everything at the same.
Yeah, I saw a bunch of people from Linux in here, so I guess everybody.
Yeah, yeah, they have to come here. So we can actually calculate the energy of that attraction between the two. All we need is the distance between them, and this becomes a +1 and a -1. So if the value, the overall value is a negative, that's an attraction. If it's positive, it's repulsion. Because with the same, if it's two pluses, it's plus. If it's two minuses, it's plus. But if it's a plus and a minus, then the overall is a minus.
Repulsion.
Right. If they're both minus or both plus, it's repulsion. So all we need to know is what's the distance between the two centers of the charges. And there's your example, 0.276 nanometers is the distance between sodium and chlorine ions. Right? And that's what we come up with. When we do that calculation, we get a very small value for joules, 10 to the minus 19th joules. Okay, when we talk about covalent bonds, now we want to look at this. The very simplest example is two hydrogen atoms coming together to form H2. We know that this is the most stable form of hydrogen at room temperature and 1 atmosphere pressure. It's diatomic. How did it get there? Well, the attractive force for this neutral atom is based upon not transfer of electrons, but sharing. So we're gonna share electron from one atom, electron from the other.
Like covalent?
Yeah, this is covalent.
Yeah.
Yeah, this is a covalent bond.
This is stuff that I learned in Chem 1. But we've worked on harder things.
We're getting there.
Okay, so this is just the base.
This is background.
Okay, great.
Yeah.
But why do I know this?
And when we represent them as probabilities for the electron density around the atoms, most of the electron density will be between the two nuclei. Okay. That's what all those red dots mean. There's a balance that is maintained when these two atoms approach one another. As they get closer and closer, they're going to feel repulsion of their electrons, and they're going to feel repulsion of their protons. But they're also feeling attraction between the electrons of one and the proton of the other. So there's a balancing act. And you get to an ideal distance apart where you're at the very lowest possible energy, which means that the proton repulsion, the electron repulsion is balanced by the electron-proton attractions. And this is probably the best way to represent what's happening when these two atoms approach one another. And this graph has, on the y-axis is the potential energy, and on the x-axis is the distance between the atoms. So the best way to view this one is not normally how you would do it. Start with the origin and move up and to the right. It's better to understand what we're trying to explain here by starting from the far right, where the individual atoms are far apart. The distances between them is infinity. And then as they approach, you see the energy start to drop. As they get closer, the energy drops down here until you get to an ideal distance between the nuclei of 0.074 nanometers. Okay. Then if you try to push them closer together, the potential energy goes way up fast, because now the repulsive forces are winning. The repulsions of the electrons with each other and the protons with each other. That's why chemical reactions are really easy to proceed, right, to form this dihydrogen molecule. But if you want to fuse the nuclei, right, and make helium like the sun does, you need very high temperatures, very high pressures to overcome those repulsive forces. Because only when you get those nuclei close enough does another set of forces take over. The strong nuclear force then takes over, and that's when they bind. And they give off a lot of energy. I mean, huge amounts of energy, according to Einstein, because the mass of these two hydrogens is greater than the mass of this of that atom. It's called the mass deficit. So if this has less mass than that, what happened to the mass? We turned it into energy. So that's the power of fusion. Okay, that's not part of the lecture. I threw that one in for free. Okay, so we end up with a bond at an ideal distance between the nuclei, where those forces balance one another. Okay, just a reminder, ionic bonding, you transfer electrons. Covalent bonding, you share electrons between the nuclei. But there are intermediate cases. In other words, up to this point, we've said, well, okay, if a metal and a non-metal combine, it's going to be an ionic bond. And that's still true. But every bond, whether we call it ionic or covalent, has characteristics of both in it. Some have very little ionic character. Some have a lot of ionic character. Some have very little covalent character, and some have a lot of covalent character. But there's no such thing as a pure ionic bond or a pure covalent bond. I mean, even if you get two atoms that are exactly alike, like the two hydrogens, you still have some ionic character. It may not be much, but it's there. So if we form a covalent bond and we have exactly the same elements, the two atoms binding together, we obviously consider that a non-polar covalent bond. In other words, the distribution of electrons in this between these two hydrogen atoms is spread equally. Right? So it's not polar. Should I go shut the door? They're meeting next door in the biology lab. That's the problem.
You can still hear.
Through the walls, yeah.
Oh my goodness.
Okay. There's essentially no charge separation, which means they're in the covalent bond where we know that they're sharing, there's no polarity to speak of. When there's a difference in electronegativity between the atoms of a sufficient magnitude, then you can get a polar covalent bond where there is an uneven sharing of electrons, and you get a slight negative on one side and a slight positive on the other. Example, hydrogen fluoride gas. Fluorine is the most electronegative atom in the chart. We did electronegativity, didn't we?
Yeah, but that's the most.
Yeah, on the Pauling scale, it's 4.0.
Okay.
There's nothing higher than that.
Okay.
So this bond is going to be polar in that direction.
Right.
Okay. That is definitely a polar covalent bond. And we can actually measure the polarity of that bond. And with this slide, we're showing that between those two plates, our sensitive equipment can tell just how polar that bond is. I don't know how they do it, but it can be done. So in review, the chemical bond in general is described as a force holding two atoms together that makes them function as a single unit. Why do they bond? Well, what we do know is that the energy of the combined atoms is lower than the energy of the individual atoms separate from one another. That's one of the driving forces. Now, how do they bond with each other? Well, they can either share electrons or they can transfer electrons. Right, so that's the simplest way we can put it up to this point. Well, maybe we didn't talk about electronegativity yet, because I've got slides on it now.
We talked about it, but we haven't had like a test on it, but
I don't know.
you've mentioned.
We haven't described it in terms of the periodic table.
I have never heard the fluorine was the most electronegatives, probably not.
Okay. So you're going to get it now.
Okay.
This concept was studied by lots of people in the late 18th and early 19th century. And what they were interested in doing was trying to say, all right, if these atoms, we know that molecules and bonds are polar or nonpolar, right? We know that they react a certain way in an electric field. And some of them orient themselves a certain way in the field and some of them don't. Right? So if we put nitrogen gas in there, which is two nitrogen atoms, we get no response whatsoever in that electric field. But if we put hydrogen fluoride in there, we get a response, and it can be measured. Right? So what we're trying to do is explain why that is. So they started developing Avogadro, Berzelius, and several others came up with this idea of electronegativity. And it was an attempt to describe the strength of pull of one atom against another in a bond on the electrons that are in the bond. Right? It doesn't have anything to do with atoms. I mean, we have the electronegativities listed in the form of a periodic table, but those values are determined for those atoms bonding with something else. All right. Okay. The most useful system and the most widely used system assigns numbers to the atoms from 4.0 maximum is fluorine down to about 0.7, which would be cesium or francium. So you can see cesium and francium are the lower left, fluorine's in the upper right. And so the trend there is like ionization energy. Lower left to upper right increasing. So the more electronegatives are in the upper right, the lowest electronegatives are in the lower left. Pauling proposed this scale in 1932. And along with that scale, he also published a book called The Nature of the Chemical Bond. And based on, and what he was trying to do was synthesize everything they knew about the chemical bond at that time, in the mid-30s, or maybe in the 40s. Can't remember what. Anyway, he was able to bring everything together that they knew and give a coherent description of what the chemical bond was based on our current knowledge. And it was so widely accepted and answered so many questions well that he got a Nobel Prize for it in 1954. He also got a second Nobel Prize, a Peace Prize. That first one was in chemistry. The second one was Peace Prize in '62 for anti-nuclear proliferation work. So Pauling's method, and this is an oversimplified version, and you're not going to have to do any calculations with this equation because it is really simple. How the electronegativities were determined. First, what we had to do was, what's the expected energy of a bond between two atoms? And in this case, we're using hydrogen as our anchor. So hydrogen with something else, the expected the expected energy of that bond would be the energy of the HH bond plus the energy of the XX bond divided by 2. And And that would be the expected energy of the HX bond. Okay. And all these values are relative to one another. Then what we want to do to determine the electronegativity is to take that value for the expected energy of the HX, the expected, and compare it to the actual measured strength of that bond. Right, so we take the energy of the HX actual, that is, we measure it, and then this is the theoretical, and we subtract the two. And that delta gives us a value of that's prorated to electronegativity. If the electronegativities of H and X are identical, then delta, this would be 0. Because our actual measured would be the same as the expected. Okay. That's just a sort of a skipping across the top of the waves and description of where electronegativities come from. What we want to do is use them to answer questions. So this mentions what I've already told you. In the periodic table, the elements have the lowest electronegativity in the lower left-hand corner. So they increase going up a group, or they increase going right in a period. So lower left to upper right, we get an increase in electronegativities. To a maximum of 4 for fluorine and a minimum of 0.7 for cesium and francium. And there's an artist's rendition. Notice that it's the change is fairly consistent for the representative elements. Those in the s orbital filling and those in the p orbital filling, you get a fairly consistent lower left to upper right increase. Once you get into the transition metals, then you sort of get a hump. They're a little more difficult to deal with. But the values can still be calculated. Right? We do have values for them. So we can compare the values of one to the other. And if you take, this is for 2 atoms in a single bond. If you take the value of the electronegativity of one and subtract the other one, and if you happen to get them reversed and you get a negative number, just throw the negative away. All we want is the absolute difference. So if you calculate the difference between the 2 atoms, we can tell with experience, right? We can tell whether the number represents an ionic bond or a nonpolar covalent or a polar covalent bond. So that's what we want to do next. Well, actually, what we want to do next is sort of not a semi-quantitative even, it's a qualitative approach. Okay. Which one of these would be more attractive to electrons, lithium or fluorine? Well, they're in the same period. Lithium is the far left, fluorine is the far right, so fluorine should have the strongest attraction for electrons. Okay, they're in the second period. How about if we compare fluorine and iodine? Well, iodine's below fluorine, they're both halogens, but iodine is below, so it's going to have a lower electronegativity, and fluorine again wins. Now, why is that? Let's see, do I have a slide on that? Yeah, okay. As you go across the period, and this is a similar argument to the ionization energies. As you go left to right, you're adding electrons and protons at the same time, right? 1 electron, 1 proton as you move to the next element to the right. The electrons are going into similar energy levels, right? Principal quantum number associated with that period. But you're also adding an extra proton. So the electrons are still right about here, and you're adding more positive charge. So you're actually increasing the effective nuclear charge as you go from left to right. And if you increase that positive charge, then you're drawing negative charges more strongly. So when you bond with something, it's going to be a stronger as you move further to the right because of that effective nuclear charge increase. Up and down a group. In this case, as you go, let's go from top to bottom. If you move down a group, then you're adding protons, but you're also adding electrons in higher and higher energy levels. So what you're doing is, as you get these electrons further away, you have more negative charges in the core that are shielding the positive charge from inside. So you're effectively decreasing the nuclear charge that other atoms would see in a bond. So that's kind of the way, that's the most popular way of considering why the trend. I mean, we know the trend because the measurements have been made, and this is our explanation for them. Okay. All right, so like I said before, every bond has covalent and ionic character. The smaller, as you calculate the delta between the electronegativities of the two atoms, as that value gets smaller, the covalent character versus the ionic character increases, and vice versa. If that delta becomes larger, then you start to favor the ionic character. And these are sort of rules of thumb. If the electronegativity difference is 0.2 or less, then we say that's a nonpolar covalent bond. If it's between 0.3 and 1.4, we say it's a polar covalent bond. And if it's greater than 1.5, it's ionic. Now, I left out, for some reason, there's not a column in there to distinguish between non-metal versus metal nonmetal. Because if you've got metal and nonmetal, and the electronegativities between them are less than 1.5, you may still have an ionic bond.
The metal and non-metal.
Yeah, if you have metal nonmetal. This 0.3 to 1.4 is strictly applicable to covalent bonds. But if you have a metal, and that means non-metal nonmetal. But if you have a metal nonmetal, I think you can dip further into that value below 1.4 and still have an ionic bond if it's a metal nonmetal. I'm not sure why the slide is incomplete. All right, let's see if we can use what we've learned to arrange these as most to least polar. So the most polar would be the pair of atoms that are furthest apart from one another in the periodic table. And if we look, let's see, they're all attached to fluorine, so all we have to do is look what order are they in the table. Carbon, nitrogen, oxygen. Carbon's furthest to the left, so it must be the most polar. And then the least polar would be the one that's closest to fluorine, oxygen and fluorine. And nitrogen's in the middle. That was an easy one. Okay. How about carbon, fluorine, nitrogen, oxygen, and silicon, fluorine? Well, if we look at the, right, which one's furthest apart, furthest from its neighbor? Carbon and fluorine are pretty far apart. But silicon, right, silicon moves down a level and is the same distance as carbon.
Carbon.
Silicon.
Yeah.
Silicon and fluorine.
Carbon and fluorine.
And then carbon and fluorine.
And then nitrogen and oxygen.
That's what I'd say too. Okay. The last one. Felt. The easiest one to do here, the least is chlorine.
Mhm. The second least is, acid chlorine, sulfur.
Would be boron chlorine, sulfur chlorine. Yeah, sulfur chlorine would be next. And then boron. Chlorine?
Mhm.
Yeah, that's what I'd say too. Yeah. Okay. So let's try again.
Yeah, give some test questions like that.
Yeah.
All right, so for this one, which of the following would be the least polar, yet still be polar covalent? Right. So we know that oxygen is not going to be polar at all, so we throw it out. Magnesium and oxygen are not covalent, right? So we can throw that one out too. So we really only have to compare carbon oxygen, silicon oxygen, nitrogen oxygen. The least polar is the one that's closest together. Nitrogen and oxygen. Yep. In fact, the difference between the two would be 0.5. Right, 3 and 3.5. Okay, which will be the most polar without being ionic. Right, so magnesium, oxygen, throw that out again. The most polar would be the furthest apart. Let's see. Carbon, oxygen, silicon, and oxygen. Yeah, I think so. Wait a minute. Oh, okay. So in this case, we need to do a calculation. Silicon and oxygen would be 1.7. All right. That's in the ionic range. All right, let's go back.
Oh, okay. Yeah.
Yeah,
Okay.
greater than 1.5.
Oh, okay. I think.
Trick question. So we have to go back, we have to go down to carbon oxygen as covalent and yet polar. Wait a minute. There it is. One
So
slide.
what would silicon and oxygen be?
It would be ionic.
It's 1.7, 3.5 minus 1.8.
Okay, without.
Yeah.
Okay.
Now that
Open to.
that kind of flies in the face of our rules of thumb up to this point, because silicon's not a metal. It's a metalloid. So I guess that's how we get away with it. Metalloids and non-metals, sometimes they can behave like. Okay. So when we've got a bond, we can speak of it in terms of what direction the charge distribution is in and the magnitude of the charge distribution. And we call that a dipole moment. That word moment is drawn from physics. Anytime in physics you have a force acting in a certain direction, like that, with this as its anchor, that's considered a moment. Right? It tells you what direction the force is pulling and how big it is. And so if I have another force that's going down here like this, just a little one, I may want to know what's the resultant, right? When these two forces are pulling at the same time, what is it equivalent to? And in order to do that, we draw a parallelogram. Let's see. This one would be parallel to that one. This one would be parallel to this one. And then we draw a connector between that and here. And that's what these two result in. That point feels as if it's being pulled, this force in that direction. And we can do that in chemistry too. All right. And we use an arrow. I drew that earlier, but I forgot that I hadn't described it yet. So if we have a molecule like water, which is shaped like this, right? Oxygen is more electronegative than hydrogen. So for that bond, it's going to be positive on this end, negative on that end. And the same thing for this one. Right? So if we take the resultant of those two, we have an overall in that direction for the water molecule. And sometimes we put that little Greek delta, right? Slight positive charge here, slight negative there to balance it. Okay. All right. Now, when we want to determine whether a molecule is net, polar or nonpolar, we need to know two things. One is, are the bonds polar? In this case, yeah, they are. And then we need to know the geometry. Because if we have a molecule that has a central atom and then it has two atoms here like that, right? So these are identical atoms. And let's say that these are more electronegative than X. So we get a moment that direction for this one, that direction for this one, but they're equal and opposite. So they cancel each other out. This is a nonpolar molecule, even though the bonds are polar. So what we're saying is you got to know two things when you're trying to determine polarity of a molecule is, are the bonds polar? Okay. And the second is geometry.
Great.
Okay. And we're going to do that for the day's over. We're going to look at molecular geometry, I think.
Like how the molecular plays?
What's their shape?
Yeah.
The geometry of the molecule. Yeah. So this is our water example. And it shows that the overall polarity is negative on the oxygen side, positive on the hydrogen side. That's why the boiling point of water is not minus 20 degrees, but 100 degrees, because it has those intermolecular attractions that hold them down and increase the amount of energy required to break those intermolecular bonds. Carbon dioxide, on the other hand, is like this one. It's polar toward either end, but they're equal and opposite, so they cancel each other out. Okay. We need to know something about regular shapes. Right? Molecules that are like this are going to be linear. Molecules that are like this with three Y's are going to be triangular. And the combination of words we use for this one is trigonoplanar. It's in a triangle, right? That, but they're all in the same plane. And if we have 4 attached to the X, we have, let's see, we have a Y up here, we have a Y down here, a Y down here, and a Y in the back. Right? So we have a bond there, a bond there, a bond there, and a bond there, and it forms this triangular base pyramid. And that's, in geometry, that's called a tetrahedron. All right. So back to the idea of why these bonds formed. And I'm going to pick up where Kyra left off. Electrons. Bonds form because of the electrons. And what each atom is trying to do is to work its way to an electronic configuration, right, that's stable, and that means noble gas configuration. So for the second and the third period, the number of valence electrons, remember the ones in the highest principal quantum number level, you have 8 electrons. So for the second period, you're going to have the valence electrons are going to be 2s and 2p. You can have 2 electrons here and you have a maximum of 6 there. That would be the valence shell for a noble gas. In the third period, it'd just be, we just move down one. Okay? So that's where the octet comes from. 2 plus 6 is 8. Everybody's trying to look like a noble gas, at least in the second and third period. And even in the third period, you have some deviations. But this is where we're starting. It's from this octet concept. There are exceptions to the rules, and I'm going to show you a few of them. But first, what I want to do is look at the most common charges on some of these ions. 10, for example. Right? What's the configuration of 10? Well, it has a 5s2. It has a 5s2. And then we work back, it also has a 4d10, and it has a 5p. Excuse me, 5p2. You're right. 5-2. And it has a 5s2 over here. There we go. And then when we back up, let's see, it has krypton as the core. 36, is it? Yeah, 36.
So that's much easier than doing the thing that was on the test.
Yeah, I agree.
Yes. And out of all the elements, you gotta give us 10. Go all the way down and across.
Do what?
Nothing.
So the reason I draw this out like this is these are the valence electrons right here, there and there, the highest principal quantum number. What 10 prefers is when it's trying to work its way toward the noble gas configuration, it wants to get rid of the P's because they're higher energy than the S's, just slightly. So that would give you, if you got rid of these two, that would give you a 2 plus for 10. Right? If you then got rid of these two, that would give you a 4 plus. I'm sorry?
The whole like the whole one like on the last thing about like you said it has to be whole because it wants to get rid of the two, so it gives it
No. If it's bonding with something, it gives up those 2 electrons. Yeah. No, we're not talking about the anomalies. What I'm trying to explain is that if we look at the evidence for the charge on 10 is usually either a 2 plus or a 4 plus ion. And that's where it comes from. Lose these two, you get a 2 plus, lose these two and those two, you get a 4 plus. Okay. And lead is the same way because it's in the same group, but it's in the 6th period. So instead of 5, 4, 5 here, it has 6, 5, 6, and it loses 2 or it loses 4. And lead will also be a 2 plus or a 4 plus ion for the similar reasons. And then if you move to bismuth, right, let's see, bismuth, to the right of lead, now bismuth, we're going to add another p electron. So it would prefer to lose those 3 and be a 3 plus, or lose those 3 and these 2 and be a 5 plus. And that's what we observe with bismuth. It's 3 plus or 5 plus ions. And then tellurium, go to the left of lead, and you just back off 1 here. So it would lose 1 and be a 1 plus, or lose 3, 1 and 2. and be a 3 plus. Okay. So when two nonmetals, when they form ions, when you've got metals forming ions and nonmetals forming ions to make the bond, like sodium and chlorine, they actually transfer electrons to their neighbor, and that completes the octet for their neighbor. And if they lose an electron, that completes their octet because they back up 1 or 2 or 3 to the nearest noble gas. So that's how the ionic bond works. The covalent bond works a little different. We're still trying to look like a noble gas electronically speaking, but now we can't transfer electrons, right? Because nobody's got enough electronegativity to steal electrons from the other one. So in this case, we have to imagine ourselves as a noble gas. So if, say, let's use hydrogen and fluorine again. Okay, hydrogen's got 1 electron. How many does fluorine have in its valence shell? It's 7 from the left. It has 7 electrons, right? Let's see. 1, 2, 3, 4, 5, 6, 7.
1, 2, 3, 4, 5, 6, 7.
Yeah. Mm-hmm. So if fluorine got another electron, it would look like neon, correct? And if helium got another electron, it looked like, if hydrogen got another electron, it looked like helium. Okay, right? We can't transfer electrons, so we have to fool each other. So what we do is, let me change.
I feel the outer shell, don't it?
For hydrogen?
For fluorine. It's 7.
Yeah, it needs 1.
Yeah, just need, so you just share.
Right, so we just
Yeah.
share. Let's do it like this. There we go. So if this electron shares there, we form a single bond. That 1 line means a single bond, two electrons, 1 pair. So now fluorine thinks it has 2 electrons, or has that extra electron, and it looks like neon. And hydrogen has this one that it's sharing, and it feels like it has enough to be like helium. We didn't actually create electrons, but by sharing them, we give each other a fuzzy feeling about themselves. And they feel like noble gases. So that's the difference between ionic and covalent bonds relative to their tending toward noble gas configurations. Oh, this board erased so nice this morning, and now it's give my hand a workout. Okay. So there's also another concept, the isoelectronic series, and it dovetails into this concept of electronic configurations where the bonding occurs so that we look like a noble gas. If we take this series here, oxygen 2 plus, fluorine 1 minus, neon, sodium 1 plus, magnesium 2 plus, and aluminum 3 plus, what we see with that series is that they all have the same electronic configuration. They all look like neon. And that's called an isoelectronic series. Iso means same. You ever see those little bugs that crawl in and you touch them and they roll up into a ball? Roly-polies? Yeah. Their scientific name is isopod.
Yeah, we had to do a lab with them in biology, and we had to call them that. Call them really close to get in trouble. I was like,
Yeah. But they're called isopods because all their legs, all their feet are exactly the same. Pod is the Latin term for foot. Or is it Greek? I think it's Greek, actually. So, if we choose an alkali metal, alkaline earth, noble gas, and a halogen so that they have the same, so that they fit into an isoelectronic series, we have to make ions out of everything except the noble gas. And if this example, potassium, calcium, argon, and chlorine, they all look like argon, electronically speaking. Okay. And their configuration would be 1s2, 2s2, 2p6, 3s2, and 3p6. That's an isoelectronic series. Now, the number of electrons will be exactly the same for each one. Right? 18. The number of protons will be different. Remember, because the number of protons determines the element. Right? We can't change the number of protons. All right. So we've talked about, in the past, we've talked about atomic size trends in the periodic table. We've talked about, we haven't talked in detail about ionic radius, just to mention what happens to an ion when it loses an electron or gains an electron. If it gains an electron, it goes. If it loses one, it goes. Right? Sodium and chlorine are good examples. We've talked about ionization energy trends in the table. We've talked about electron affinity trends in the table and electronegativity trends. And those are all useful information for especially the electronegativity is talking about bond polarity. So what are the factors that influence the stability and structure of solid binary ionic compounds? And now we're talking about metal, non-metal that forms some type of crystal network, like sodium chloride. Of course, I mentioned before, if you take sodium table salt and sprinkle it on the table and take a magnifying glass and look at it, what do you see? You see little cubes, perfect little cubes. They could be real big, they could be real small, but they're always cubes. And that tells you something about their crystal structure, the arrangement of positive and negative ions in that structure. But we can quantify the amount of energy required to break up that crystal, or the amount of energy we get back when the crystal forms. Now, this term lattice energy is very specific. Remember when we talked about ionization energy, where you have an X, you add energy, and you get an X plus electron. And this has to be a gas, and this has to be a gas. Right? The amount of energy you put in. If we take this X and we add an electron for affinity, and we get this negative, then we get some energy back. Okay, so you can do the same thing for lattice energy for a positive ion in a gas and a negative ion as a gas come together and form the solid crystal. Now, this could be different ratios, but I'm just using 1-to-1 for now, like sodium and chlorine. And you get energy back. This is exothermic. But this is the general format for the equation to tell us what is the lattice energy. And the reason it's used is because there are no other interfering transitions. Right, we're going straight from gas to the solid. That's the amount of energy we get back when we do that. All right. And we can quantify it. Right? We can use Coulomb's law. That's all we're doing here. Coulomb's law. K is not Coulomb's constant. K is a proportionality constant that is specific for the particular ions that are coming together. But it has a similar format to the Coulomb's law. All right. When we're forming an ionic compound, we can go through several steps. And the reason I explained lattice energy first is because we're gonna add it into these steps of how we form an ionic compound and follow the, what do they say? Follow the money. We're going to follow the energy. So we've got this metal on this side, and it's more than likely a solid. Right? There's only one liquid metal at room temperature, mercury.
I know that one.
And we have this non-metal. Let's see, what are they calling it? They're calling it X. And a lot of the non-metals are diatomic. Right, some of them are even, let's see, phosphorus is tetraatomic, sulfur is octatomic. But for our example, we're just going to take the diatomic, right? And this is usually a gas. Okay, so what we want to end up with is this solid down here out of those. And we can follow it through different steps. It's kind of like when we were doing the forming a solution. Did we do that in here? Or did I do that with my other class?
No.
I did it with the other class. Okay, that'll come second semester.
Mhm.
So first thing you have to do is get these things broken apart. We have to change this into a gas. So we're going to change this in our first step. We're going to break all the intermolecular forces that are holding it in that solid and make a gas out of it. Then we're going to take those gas atoms, and we're going to ionize them. Right? We know what this one does. This is ionization energy. Okay. This is sublimation, right? Solid to gas, sublimation energy. Then now that we've got this separate ion gas right there, we're going to leave that for now and play with this one. Now what we got to do is break the bond between those two atoms, right? And get these individual atoms, gas, but we only need one of them, right, to form that. So here's what we're going to do that. Half a mole of this yields 1 mole of that. And all these energies are prorated to molar content. Now that we've got that in a gas, what we need to do is make a negative ion out of it. So it's that electron affinity gives us this one. Now we've got this ion and that ion. Now we can do lattice energy. There. So we've got these different energies. This one is endothermic. Got to break the bonds. This one's endothermic. You have to add energy, right, to get rid of that electron. This one is endothermic. Right, you got to break the bond between these two to get that. This one is exothermic. Because the electron falls from infinity down to some orbital, right? The highest level unoccupied orbital here. So we get energy back from that. And then when this one goes, this is also very endothermic. I mean, massively endothermic. Exothermic. What am I talking about? Back up. Massively exothermic. Okay. And I noticed the other day that this is not a good slide to use for that, because notice what's going on here. You've got complete reaction equations here. that are going together to make this, to make the final equation, where we take this one plus that one yields this one. This is more like Hess's law, because you notice individual reactions here that we've put together to make the final. It's not going through these individual steps. I think the next one is better. Well, but now we're using, we're making lithium fluoride, right? Using those same steps and actual values for each one. So this step, sublimation, we have to, solid to gas, we have to add energy. That's misleading. That minus in there is really just a dash. And that's just a dash. So once we get all those together and add them together, we get a value of overall of minus 617 kilojoules. So that means we're giving up that much energy to bring those together for this particular compound. And that confirms our earlier description of why bonds form, is because the products have less energy than the reactants. Right? If it's a minus, that means energy is leaving. So overall, we're losing 617 kilojoules per mole. That means the products are lower energy than the reactants. And this particular graph does identify those energies in terms that we've presented here. That's a better graph for that purpose. That earlier graph was more like Hess's law. All right, those are the calculations. We won't dwell on that. So we mentioned ionic versus covalent character. We can actually calculate that, although I don't think I'm going to require it. But here's how they do it. If we want to define the percent ionic character, we compare these two values. What is the measured dipole for this bond? XY. And then what's the calculated dipole moment for the X plus and the Y minus? What would it be if they were complete ions? And we ratio them, multiply by 100, and that's the ionic character. So if the measured dipole is very close to the calculated dipole, it's going to be close to 100%. And when we do that, we find that the closer the elements are to one another in electronegativities, the less ionic character. And those are the blue ones down in the lower left-hand corner. And the farther apart they are in electronegativities, you get the red ones in the upper. So that's as we would predict. All right, this is an operational definition for an ionic compound. If the compound, when melted, right, it's going to be a solid. When melted, or when we put it in solution, if it will conduct electricity, then we're going to call it ionic. We know that'll happen for sodium chloride. That's obvious. But anything else, if we can't get it in solution, I mean, if it's insoluble, then we might have to melt it. And the reason we have to do that is if you melt it, then the ions become mobile and it will conduct electricity. Right? You couldn't do that with sugar or any of those covalent compounds because, well, for two reasons. One, they don't form ions when they're melted or when they're dissolved. And the other is if you put enough heat into it, melt them, it'll probably decompose it. Okay, now we're going to try to look at a covalent chemical bond model. And remember our definition of a model, right? It's a model is a macroscopic representation of the microscopic for our purposes. So the first thing to recognize that a model is not reality. A model is a simplified version of what we think reality is so that we can manipulate it and see if there's some way we can change it to learn something about reality using the model. And models invariably accompany theories. You usually have a theory first, and then the model is formed to help visualize the theory. Actually, models can come in different formats. I mean, they can be physical models. Right? I could take the molecular models over there in those black boxes and start piecing a molecule together. That would be a model of a molecule. Or lots of models are mathematical. They describe in either simple terms or very complex terms that maybe only a computer can handle. That becomes your model. But they are, in effect, oversimplifications. And as a consequence, they're very wrong. In order to simplify and produce a model, sometimes we have to disregard some factors that might be essential. And if we do that, then the model is going to be very wrong or only applicable in very limited circumstances. Models tend to become more complex over time because we're trying to make the model fit the real world. And if we start from here, but the real world is over here somewhere, we've got to change it and change it and change it, tweak it and tweak it until we get here. Sometimes we never make it. In order to use a model properly, we have to understand the underlying assumptions. We have to assume certain things before we can actually construct a model. And that's just so we don't misuse it. Right? Perfect example of that is climate models. Right? There are 30, 40, 50 of them out there. Most of them are mathematical. And they're all wrong. Every one of them. They never predict how the climate will change. Right? So whoever's using them, actually they're misusing the models. Mm-hmm. And in fact, what they do is they tweak the model to give them the answer they want. So if they say the temperature over the next 10 years is going to go up 4 degrees Celsius, right? They'll tweak the model so it'll give them that answer. That's why they never work, because they are disregarding the underlying assumptions. That's just one of the factors that makes them wrong. There are a whole host of factors. But models are also good for giving us information about the real world. In other words, when we find a model is wrong, it doesn't work, then the best thing to do is try to understand why it went wrong. That can teach you something about the real world. So what do you do when a model stops working or when a theory stops working? Either way. Well, you can restrict its application. You say, okay, we know that it doesn't work over here, it doesn't work over there, but it works in here. So we're not going to use it anywhere else but here. A perfect example is, let's see, do I have it there? Under certain conditions, yeah. Newton's laws of motion, right? Have you had physics? Okay. First law, so Newton's first law is what? An object in motion tends to remain in motion unless acted upon by an external force. Or an object at rest tends to remain at rest unless acted upon. A second law is force equals mass times acceleration. And his third law is, painting myself into a corner. Oh, I got it. For every force, there's an equal and opposite force. It's the action reaction. That's the third law. And then he came out with the law of universal gravitation. But these Newton's laws are only good within certain ranges of mass and size. If we get really, really big, like a black hole size, Newton's laws just completely fall apart. They don't work. Or if we get really, really, really small, like the size of an atom or the size of an electron, subatomic particle, they don't work there either. So we need a new theory. Down to the very small, we use quantum mechanics. Now, at the very big, we use relativity. But we know that, so we restrict Newton's laws uses. Now, most of the stuff that we're interested in, right, they work fine. Right, if you want to know how much force it takes to stop your car when it's moving at 60 miles an hour versus 30 miles an hour. Well, we know that it's going to take 4 times as much energy from your brakes to stop your car from 60 as it does from 30. We can modify the model to accommodate the new conditions, right? And that's what a lot of researchers do, because it's like they're children, right? When they come up with a theory, this is my beloved child, and I'm not going to give him or her up. So we modify it until it's just ridiculous. If it goes too far, then eventually what might happen is we throw it out and start all over again. The last time I checked, physicists were proposing 26 dimensions for space, in addition to length, width, depth, and time. And those are all mathematicals, because we don't see that in the real world. But some of them just need to be thrown out and start over. Perfect example is J.J. Thomson's plum pudding model of the atom. Right? Once Rutherford did his gold foil experiment and determined that the atom was really a nuclear atom. It had protons and neutrons right here, electrons out here. Then the plum pudding model was dead. It could not be sustained. All right. How are we doing? Got a little over an hour. What is a bond energy, right? Now we're talking about actually determining the strength of each bond. In the beginning, we said, okay, what is a bond? Well, a bond is the force that holds atoms together. So we're going to try to quantify that value. What is the energy that holds 2 atoms together? Well, that's what's known as the bond energy. And the bond energy is the amount of energy that we have to add to that bond to break it apart. So it's going to be a positive value, right? It's adding to the system. But we also know that if these are separate atoms and they come together in a bond, they're going to give up that exact same amount of energy. Right? So if we learn it one way, we know it the other way. We also know that when a single bond is formed, it's a pair of 2 electrons are involved. A double bond is another pair, so that's 4 electrons. A triple bond is 6 electrons, or 3 pairs. And we represent them with a line. Right? So if we have oxygen bound to another oxygen atom, it's a double bond. If we have a nitrogen bound to another nitrogen, it's a triple bond. Or if we have, like before, hydrogen bound to hydrogen, it's a single bond. What else do we know about those bonds? Well, we know that this one is stronger than that one. And that one is stronger than this one. It takes more energy to break that bond than it does this one. It takes more energy to break this one than it does either one of those. Now, it's not a linear progression, right? It doesn't take twice as much energy to break this bond as it does that bond. It takes less than twice. And this one, it takes less than 3 times. And there's a reason for that. We haven't got to that discussion yet. We also know that the bond becomes shorter the stronger the bond. So this double bond between oxygens is going to bring those nuclei closer together than these two hydrogens. Or actually, a better example would be you can have single bonds between two oxygens, right? Hydrogen peroxide, for instance. So this bond, these oxygens are further apart than those oxygens. And this bond is weaker than that. And that's not linear either, those distances.
So the triple bond closer together too?
Say again?
The triple bond is closer together?
Yes. Yeah, much closer. In fact, nitrogen, that triple bond between the two nitrogen atoms is so strong that it's very difficult to get them apart. Right? And plants depend upon fixed nitrogen, we call it. Nitrogen in a form that they can incorporate into their cells. Right? They can't do it with this nitrogen. The bond is too strong. They need something like ammonia or ammonium ions or nitrate ions. A fixed nitrogen is what we call that. In order to break that bond and allow you to form these compounds, you need a special enzyme system. And green plants don't have it. So what some of them do is they form a symbiotic relationship with microorganisms that can do it. Right? So that's where we get legumes, like clover, soybeans. They have nodules on their roots. And if you pull one up and cut it with a knife and it's pink, then it's active. Okay. Those microorganisms for, let's see, the genus that's common among those are what's called rhizobium. And those little bacteria have the enzyme systems to break that bond and fix it into something that the plant can use. And then the plant supplies them with energy. So it's a symbiotic relationship. All right, let's get back to bond energies. We've got this list of bond energies. Start upper left-hand corner, hydrogen-hydrogen bond is 432 kilojoules for that bond. So a mole of those bonds would require 432 kilojoules to break those bonds. And it's got all those single bonds down the left-hand side. Well, so there's another row, nitrogen, 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 nitrogen. And then eventually we get over here to double bonds, carbon, carbon, triple bond, carbon, carbon, oxygen, oxygen. You got all these values for the single and multiple bonds. And since we know those values, we can use those to calculate the enthalpy of any reaction. All we need to know is how many of each of the bonds there are in the reactants and the products. And we can actually calculate the enthalpy for that reaction. So before we had an opportunity to determine the enthalpy of an unknown reaction by Hess's law, right? And that works. But we can also use the bond energies to do that same calculation. And it's very accurate. We talked about that already. So this formula is the one we use. So if we want to know the enthalpy for a reaction, we want to sum the bond energies of the reactants. So this is the total energies of the reactant bonds. And then subtract the total energies of the product bonds. Notice in this case, we don't put the products first and the reactants second like we have done in the past. The reason for that is because these bond energies are positive to start with. So we have to do them in this order to come out with a proper sign for the enthalpy. We're going to break the bonds on this side. In fact, this is probably easier to understand. We put the energy in and break the bonds on this side, then we get energy back. So positive values here for the bonds with a negative means that we get energy back away from the system. And if you add them all up, then you'll get the enthalpy. Example would probably be better to do. So here's an example. This molecule, CH3N first, like that, can be made to produce this product. Now you may have wondered, aren't those the same molecule? No. The way we write organic molecules, this one, these hydrogens are attached to that carbon. And that carbon is attached to this nitrogen with a single bond. And then we got the triple bond. Okay, so we do the same thing on this side. This part's the same over here. Now this carbon is attached to that carbon. And then we get a triple bond. Okay, so essentially that's the only difference right there. We've got this carbon hydrogen, we've got 3 of them there, we got 3 of them here, same here and here. We've got nitrogen and carbon triple bond is the same on both sides. The only difference is this one right here and this one right here. So what you can do, if you want, is you can take 3 carbon hydrogen bonds, 1 carbon nitrogen, 1 nitrogen triple carbon, and add those all up, and then subtract all of these. Or you can recognize the fact that this is, nothing's changed for this one, and this one, and this one. These are the only ones that have changed. So all you need is the carbon nitrogen, which is 305, and subtract the carbon-carbon single, which is 347. Right? So 5 from that is, this is going to be negative number because that's bigger, right? So we got a 2, and we got a 4. Negative 42 kilojoules. Okay, let's see if I did it right. Yeah. Okay. Now, of course, if they're all different bonds, you know, you got things flopping around and you take 4 or 5 reactants and make 3 or 4 products, then you got to do them all. But for illustration purposes, this is fine. Now, if I were teaching this in a 2 classes per week, this is where I would break. But we're going to go ahead with it now. And talk about the localized electron model, which is part of the valence bond theory. So remember I said, usually you get a theory first and then you devise a model to use the theory. So we've got the valence bond theory. And then from that, we get the localized electron model. All right, so what do we mean by valence bond? It's trying to describe a bond between 2 atoms. And in doing so, we're interested only in the valence electrons, right? And the orbitals that they occupy. We know how to write an electronic configuration and we know what the orbitals look like, we think, mathematically speaking, right? In this case, we've got 2 dumbbells, so those are probably p orbitals. And what we see is with this valence bond theory for bonding, that's redundant, is that the orbitals of the 2 atoms overlap. And that's where we get the sharing of electrons. And the only electrons involved in the bonding are the valence electrons. Okay, that's true for the valence bond theory. Now we're going to move on to another theory for the next exam, not for this one, but for the next one. And I'll give you a teaser. We're going to take all the electrons of every atom in the molecule, and they fit into the model. It's called the molecular orbital model. All right, so that's where we're headed, not for this exam, for the next one. So there were a lot of people that worked on this, and the localized electron model uses a quantum mechanical system. to describe the orbitals and the overlap of the orbitals. And a lot of people worked on it. Right? There's Fritz London. I think he was the one that's responsible for London dispersion forces. I don't know about Heitler. Linus Pauling, he's been around forever. Well, not anymore, but he was. I think he's passed. Okay. So we need our assumptions, right? What are we saying the localized electron model tells us about the molecule and how it bonds? Electron pairs are assumed to be localized on a particular atom or in the space between the atoms. So if we drew ammonia would be like this, and it would have like a hydrogen in the back, and then it would have a hydrogen here and hydrogen here, and the base would form this triangle. These are bonds, those are not bonds. But we had an extra pair of electrons there. So what the localized electron model says, the electrons are localized either on an atom, they belong to the atom, or they're shared between in bonds. Right? So they still owe their allegiance to individual atoms. And that's an important point when we go to the molecular orbital model. These are called lone pairs. Lone pairs always belong to one atom. Bonding pairs are between the atoms. So these two pairs of electrons, they're shared between these two atoms. These two are shared between those two atoms, and so forth. Those are bonding pairs. If we have a double bond, we have two bonding pairs. Triple bond, we have three bonding pairs. Okay, this just emphasizes that part 1 and part 2 here, number 2 and 3, are what we're going to cover in this chapter. And part 3, or number 4, is going to be held for my chapter 9 and the rest of your chapter 9.4 to the end of that chapter. Okay, so you don't have to go past 9.3 for this test. All right. It can get really complicated. So thanks to a chemist by the name of G.N. Lewis, who was an American, he proposed a way to think of atoms using their symbols so that we can get an idea of what they're likely to do when they bond under these models, under this theory and that model. So in order to do that, he assumed that every atom, particularly the second and third period, wants to look like a noble gas. And what you do is you write the symbol and you give it the number of electrons it has in its valence shell. Right, we can do that. And use dots. So nitrogen is 5 from the left. All right, so 1, 2, 3, 4, 5. That's 5 electrons around it. It can have a maximum of 8. Right, we're trending toward the octet. So it needs 1, 2, 3 more electrons to complete its octet and look like neon. The exception to that is hydrogen. Hydrogen only has one s orbital, so it goes by the duet rule rather than the octet rule. Once it gets one electron, it's done. Fluorine, of course, when you get two fluorines together, right? This fluorine has 1, 2, 3, 4, 5, 6, 7. And this fluorine has 1, 2, 3, 4, 5, 6, 7. So all we need to do is share these two electrons, and now we have a bond, and each one has a noble gas configuration. Supplies its octet. So when we count the electrons around this atom, we say 2, 4, 6, 7, 8. So it has an octet. That's a Lewis dot structure. Single bonds, double bonds, covalent bonds, triple bond. So when we write a structure for a molecule, we need a method, right? So that we can use all of our valence electrons, not create any, not throw any away, and create a Lewis structure for that molecule that's valid, right? So what we do, let's see. Yeah, we got water as an example, right? There it is in black and white and blue. But if we have water, we start off with a molecule that we know exists. It has to be that way. And then we count up the number of valence electrons for that whole molecule, right? Each hydrogen has 1, right? So that's 2. Oxygen is 6 from the left, so it has 6. That means we have 8 electrons that have to be positioned somewhere in that molecule. Next thing we have to do is decide which one is the central atom. All right. In this case, it's easy. Hydrogen can't be the central atom because it can only form one bond. Right? It couldn't form a bond with oxygen and the other hydrogen. So that one's easy. Oxygen's the central atom. And then we form a single bond with the others. That's 2, 4, minus 4. We've used 4 electrons. Now we have 4 electrons we have to position.
4.
Huh?
All of those before.
2, 4. Each bond is 2 electrons.
Okay.
Yeah. So that's 4 that we've used. So now we have 4 electrons that we have to do something with. Well, we can't put them on the hydrogen because it's got its duet, right? 2 here, 2 here. So you move from the outside in and work your way in. So oxygen's next, it has 4 electrons. Okay, it has 2 lone pairs. That's a valid Lewis dot structure for water. And that's what we're saying here. Okay. We're always trending toward the octet, except for hydrogen. Right? So if we have PBr3, let's do that one. PBr3, phosphorus is akin to nitrogen, so it has 5 valence electrons. Bromine is a halogen, it has 7, so 3 times 7 is 21, right? That's 26 electrons. Now, which one is the central? We could make bromine the central, but it's probably phosphorus. And the way I tell is I see which one is the least electronegative. Probably phosphorus. It's to the left of bromine. So we put phosphorus in the middle, and we form a single bond with each of the bromines. That's 2, 4, 6. So we have 20 electrons that have to be positioned. Work from the outside in. I need to take a break. Go to the little boy's room. Be right back.
We had told you about the flooding. At our company, like, to do all that. Well, it was just right, but I think
This goes to 8.13.
that is in the linear chapter 9.1. We split in that chapter 9. Chapter 8 and chapter 9.
That's our, this is our chapter. Chapter 8.
And it's in the Lord's Morning. Portion 9. Then 13. Came in a new way.
I like to mix it up. My father for a while sold insurance. Find his way around in a new city, and we moved quite a bit. He would purposely go out and get himself lost so he could so he could find his way back, find new ways to go places.
That's funny.
Okay. Yeah.
Okay, we're doing chapter 8, so 8.13,
Yes.
and then we're doing chapter 9.1 and 9.3.
Yeah. In your book,
Yes.
chapter 8 and 9.1 to 9.3
Okay.
covers everything that we're talking about.
All together, box, like is it?
It's what?
Is it all together at the other school?
Yeah, it's in one chapter. Chapter 8 is everything that we're just talking about here. And then chapter 9 in my textbook covers what we're going to do in the next exam. Okay, so we're down to 246. We have 20 electrons. So we start placing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So now we have 2, 4, 6, 8. We have an octet around bromine. And we only used 18. We got 2 electrons left over. They have to go on the central atom because there's no more room around here. So that's your Lewis dot structure for phosphorus tribromide.
Oh, okay, I did that, because the bond with the.
And you can count them up again. 2, 4, 6, 8. 2, 4, 6, 8, 2, 4, 6, 8. So 3 times 8 is 24, 25, 26. Hydrogen cyanide is a little different. Well, let's do that one. Hydrogen cyanide. So we have 1 electron for hydrogen. We have 4 for carbon, I believe. Yeah, 4. Nitrogen has 5. So we have 10 electrons that we have to position. Now, which one's going to be in the center? Well, Hydrogen can't be, of course. Carbon's to the left of nitrogen, so we put carbon in the center.
Carbon's to the left.
Yeah. It's less electronegative, so it goes in the center. And then a single bond, well, the hydrogen's done. It's got its duet. And we've used 2, 4, 6 electrons left over. We start from the outside in. Can't put any around hydrogen, so we go back to nitrogen. 6 electrons. Okay? But we're not done, because carbon doesn't have an octet yet. It's only got 4 electrons. So how do we make it have 8 electrons without depleting nitrogen? Yeah, we take these 2 and these 2 and make a bond. Okay, so that gives us like that.
That's so rude.
Oh. So now we have 2, 4, 6, 8 around nitrogen, 2, 4, 6, 8 around carbon, and 2 for hydrogen. So that would be a valid Lewis dot structure for hydrogen cyanide.
The dots are helpful. I can see it.
Skip that part. Let's skip this one too, because I don't want to run out of time. Lewis dot structures for these guys. And your review document has more examples, of course, for you to work on.
Go back.
Oh, okay. She's not gonna miss much. If we do carbon dioxide, that's a good one. Carbon dioxide. So carbon has 4. Oxygen has 6 times 2 is 12. So we have 16 for carbon dioxide. Carbon's in the middle. It's to the left of oxygen. So put carbon here, oxygen there, oxygen there. So that's 2, 4. It's 12 electrons. So if we put 2, 4, 6, 2, 4, 6, we've used up all of them.
So that's
Okay.
good.
I'm sorry.
So that's fine. Okay.
Yeah, well, we still need to make an octet for carbon.
So you could share them.
Yeah. The best way
You
to
do one from each?
the best way, yeah, is to take one from each. And but theoretically, you could do you could take 2 from here, 2 from here, and make this one. With 2 lone pairs around each oxygen and a double bond. Or you could do this one.
Oh,
Just take 2 from both sides, from one side.
it doesn't look as good.
No, and it's not the best way. And I'm going to show you why in just a second. I'm going to leave that one up there because it's going to be part of my discussion as we go. We'll come back to it. But in the meantime, the octet rule is valid wherever we can make it work. But there are some cases where we know we have a molecule like boron trihydride. We know it exists, but we can't make an octet for the boron. All we can do is that boron with 6 electrons around the boron. So the boron in this case is deficient in octet
Why can't you compare them?
because we don't have enough electrons. Right? If we do the boron trihydride, right, we have 3 here, and boron is 1, 2,
Okay.
3. Right? We only have 6 electrons. So when we do this, they're all used up. Right? And we can't fight nature. I mean, it's deficient. but we know it exists. Right? That's one possibility. Deficient octet. The next possibility is exceed the octet. Right, so if we do, let's see, sulfur tetrafluoride. Let's see, sulfur is in the oxygen group, so it's 6. Fluoride 7 times 4 is 28. So that's 34 electrons. So we put sulfur in the middle, it's to the left. We have 4 fluorines. Right? 2, 4, 6, 8. 26 electrons. So we put 2, 4, 6. Put 6 around each fluorine times 4 is 20. 6 times 4 is 24, isn't it? Okay. We got 2 left over. We can't put any more on fluorine, so we have to put that one on sulfur.
How does sulfur make any work? She's already got 2 words a day.
Good question. Notice where sulfur is located.
I just called her a she, I don't know why,
That's all right.
but.
Sulfur's in the 3rd period, right? So,
The 3rd period.
yeah,
I got you.
yeah, 3rd period, which means what? If N equals 3, L can be what? 0, 1, or 2. S, P, D. Sulfur has access to d orbitals,
Wow.
and that's where those 2 go, in the d orbitals. You don't get that.
I didn't ever know what that, I didn't. Now that you've drawn it out, I understand that a lot more because I didn't understand that very much.
If you stick in the 2nd period,
I can't.
no, they can't.
Right, 0, 1.
And then arsenic pentabromide is a similar situation. In this case, we don't have any extra lone pairs. We actually have 5 bonding pairs. So that's 2, 4, 6, 8, 10. We have 10 electrons for arsenic. And arsenic is in the 4th period, so it has access to 4d orbitals. Okay. All right. So that's where we exceed the octet. Now, in the interest of time, I'm just going to show you this one.
Yeah, I think I got it.
You probably got it, yeah.
Yeah.
Right. This one, phosphorus pentachloride exceeds the octet. Boron trifluoride is good. The thing about boron trifluoride is, where do you put that double bond? Right? All those fluorines are equivalent, so to speak. You could put it on the lower left or the lower right. So you actually have 3 possibilities there. And sulfur hexafluoride has 12 electrons. Okay, we don't need to stop there. Now, when you have more than one valid Lewis dot structure available, one of the ways to deal with it is with a process called resonance. You draw all of the possible structures, and as long as they're equivalent, except for the movement usually of a double bond, and then you put the double arrows between them, and they are said to resonate among those different structures. That's one of the limitations of the valence bond theory and the localized electron model, because we can't draw them as, in this case, nitrogen, oxygen, oxygen, and oxygen with a charge. Don't forget the charge, because without that charge, you don't have 24 electrons. When you have the charge, then you have 23 plus 1 is 24. So don't forget that. If it's an ion, right? Sometimes we draw it like this. to show that those bonds are equivalent. But that doesn't fit in with the valence bond theory of the localized electron model, the way it's derived. We have to use whole bonds, either single, double, or triple. But this illustrates the fact that those bonds between the oxygens and the nitrogen are all the same length, all the same strength. Right? The way we've drawn them in this resonance structure says that they move around. Like at one time, a nitrogen oxygen here is short, and then it's short here, and then it's short here. It doesn't work that way. Not in reality. This is sort of a workaround that Linus Pauling proposed, this idea of resonance. What actually happens is the electrons that are part of this bonding system, they're actually spread out, delocalized around the whole molecule. And that actually stabilizes the molecule when you can do that. Right? This molecule is more stable with its 3 resonance structures than one that would be similar, if we could think of one, that only had 2 resonance structures. This delocalization stabilizes the molecule. Let's see, I don't think there's much to be gained from doing these. Now, let's get back to this one over here. How do we decide which one of these is the best? Because we know they're not equivalent. They are different structures. So we've got to decide which one would be the best. And we use a procedure called formal charge. Formal charge is not a charge. It's just a bookkeeping scheme for saying, all right, what do we suppose the charge might be on these various atoms? The way you do it is you start with the free atom, the neutral free atom. How many valence electrons does it have? Right? Oxygen will have 6 in the free atom. But carbon. Carbon will have 4. Oxygen will have 6 and 6. Okay. Then you count up how many electrons in that molecule are claimed by the atom. Lone pairs belong to the atom, right? So both of these pairs belong to that oxygen. And it gets 1 from each of these bonds, right? The other goes to the other side. So we have 2, 4, 5, 6. And you subtract that from the free atom electrons, and that's your formal charge, 0. And it's the same thing on this side, -6 equals 0. How about carbon? Well, carbon has 4. How many does it get? Well, it has no lone pairs, so it's got 1, 2, 3, 4. -4, 0. So the formal charge on each one of these atoms is 0. If we do the same thing for this side, carbon's going to be the same, right? 1, 2, 3, 4. Right? So it's 0. We know that. How about this oxygen? Right? It starts off at 6, but it has 1, 2, 3, 4, 5, 6, 7. That's a -1. This is a -1 formal charge. How about this one? That oxygen starts at 6, and we subtract 1, 2, 3, 4, 5. That's a +1. Okay. Here's where we make the choice. The one with the lowest formal charges for the most number of atoms wins. So this one's all zeros. This one's a plus, 0, -1.
Win what?
Wins the contest. Which one is the most valid?
Oh.
Right? If you can say that. I don't know if you can say most valid. It's either valid or not. So this is a valid Lewis dot structure. That one's not. Based upon formal charge. The other rule that we have to watch is if the structure has no charge, right, like carbon dioxide, then all the formal charges have to add up to 0. And in this case, they do. In this case, they do. If we did it for this one with, say, a negative here, or a 1 there, and like that, then we'd add those up, and they would have to be a -1. Okay. this is just more saying what I told you how to do it. That's all that's all we're doing there. So am I getting close? Oh no, we got three-dimensional structure, geometry.
Can we just go into 8.13?
No, we're doing the 9.1.
9.1 to 9.3. Well, this is from my book.
Yeah.
Right, so it'll be the end of that chapter. Chapter 8 in my
Okay,
in Zumdahl,
gotcha.
but in Brown, it covers
Okay.
a little
Okay,
extra.
that makes-
So what about this Lewis dot structure? What's the formal charge for this one? If we calculate the formal charge, we find that phosphorus is 5 as a neutral atom minus 4 from this structure gives us a +1 for phosphorus. All right, do the same thing for the chlorines. Oxygen, excuse me. Let's go to oxygen. 6 minus 7, and you get a -1, and chlorines are 0. I already mentioned that rule. Yeah, they always have to add up to the charge on the molecule. So if it's a polyatomic ion, it's got to be the charge. And if it's a neutral, then it's got to be 0. And this is the discussion that I just gave you over there, so we don't have to dwell on that one. That's the preferred. All right, just a word of caution about formal charges. Just be careful when using them. Sometimes the formal charge can lead to an erroneous prediction. But it's one way to get there. Right? Sometimes we have to defer to reality, right? If actual laboratory testing tells us if it told us that this is the right structure, then we just have to accept it. Okay, now we're gonna take the Lewis dot structures for our molecules, use that information in another model, the VSEPR model, and try to predict the geometry of our molecule. VSEPR stands for valence shell electron pair repulsion. That's a mouthful. What it means is that all the electrons that are in the bonds and lone pairs are trying to get as far away from each other as possible. So the regular geometric structure that allows them to do that is the preferred one. Say if we had this one, boron trihydride, that would be the best way. I mean, if you move it closer to here, farther away from that one, you get it closer to this one. So this equilateral triangle shape is the best for that molecule because the electron pairs are farthest apart. Okay, that helps us predict the geometry. And what we're really trying to do is minimize the electron pair repulsions. Now, it's also true that in large molecules, you can have a geometry at this end for a central atom, and then go to the other end of the molecule, or even next door, and get a different geometry. All right, we're going to start off with simple molecules where you only have one central atom, and then you can go from there. All right. I'm not going to spend a lot of time on this. I think it works better, I found, if I draw a table for you with all the information that's contained in these slides. Linear structures, trigonal planar, which is the boron trihydride, tetrahedral, we've talked about those, but there are others. So in order to use the VSEPR model, you have to draw the Lewis dot structure. Once you've got the Lewis dot structure, then you can count up the number of groups around the central atom. And I say groups rather than pairs because in this model, we consider double bonds and triple bonds as a single group around the central atom. So in this example, if we had this one around that central atom, you got two groups. That's it. And this would be a linear molecule because this one is far away from that one as possible, 180 degrees. Okay. So let's see. I'm going to skip this one. Skip that one. Is it going to show me? Hold on a second. Sorry, here we go. All right, so let me draw you a table. I'm going to make more room here. So in this column, we're going to have the number of groups around the central atom. All right. We can have theoretically one group, but then there's not really a central atom because they're equal. But if we have two, we can have three, we can have 4, 5, or 6 groups. That's as far as I'm going to go. You can go bigger than that, but for our purposes, this is plenty. This is groups either bonding or lone pairs. Doesn't matter. Then we're going to derive the electron geometry, the geometry that holds those bonding electrons or the lone pairs. So the electronic geometry is our next step. Then once we've got the electronic geometry, we're going to look to see how many lone pairs there are and cover those up and say, now we're looking at the molecular geometry. What is actually the geometry of the atoms in that molecule? Because the electrons, you don't see them anyway. All right, so now we're looking at the molecular geometry. And I'm not sure if I can give you examples of each one. Maybe they'll show up here. Okay. Now, if we have only one central and then another one, it's got to be linear. There's no option there. If we have two around the central atom, like this is first example here on that slide, it has to be linear, yes. What if one of them is a lone pair? It's still linear, isn't it? But if we still have two around the central atom, what's the bond angle? Remember, the bond angle has this and something else like that. In order to have a bond angle, the central atom occupies the apex. So the angle goes like that. Right? Okay? Only the bond angles are only valid for atoms bound to other atoms. We never say bond angle for lone pairs. So if we do have a central with two, then the best geometry and the angle of that one is 180 degrees. Actually, I should put it over here on this side because we're talking about molecular geometry. 180 degrees is the only possible bond angle for that molecule. If we have three groups, then the electronic geometry is what we call trigonal planar. And if all the positions are occupied with atoms, then it's also trigonal planar. Now, what are the bond angles? Well, if we have a central atom and we have like this, right? What's that angle? Well, if you go all the way around a circle, it's 360 degrees, right? So we divide it into threes. 120 degrees. Okay? If we have one lone pair right? If one of these is a lone pair, theoretically, we still have 120 degrees, but now the shape of the molecule is bent, or some books say angular, okay? If we have two lone pairs, then it's linear again, so I'm not gonna put that one up there. How about four? If we have four groups, we're looking at a tetrahedron. Okay? And the bond angle for a tetrahedron, if they're all occupied with atoms, then the bond angle is 109.5 degrees. If we have one lone pair, then we have, let's see, we have let's see. We have a lone pair up here, and we have an X in the middle, and then we have a Y in the back, and we have a Y out here and a Y out here. At those bonds, and then we sort of imagine a triangular base for our pyramid, and then up here like that, and that's our tetrahedron. And the bond angle is like this one to the X down to here, say, that's 109.5 degrees. But if this is a lone pair, what do you have? You have a trigonal pyramid. You have a triangular based pyramid. Let's see, let's go to the next slide. Yeah, there it is. That middle one is a trigonal pyramid. And what happens is lone pairs, they're not constrained by the bond. So they tend to balloon out, and they put pressure on these others. So the bond angle is usually less than 109.5. If we have two lone pairs, right? If we have a lone pair back here and here, then we have a bent molecule. That's like water. And we still have less than 109.5. Now we have two lone pairs out here putting pressure on our bonding atoms. And if we have five, we have a trigonal bipyramid. I like to draw pictures. We have a trigonal bipyramid. We have a triangle in the center. We have our central atom, right? Then we have something up here and something down here. So that's 1, 2, 3, 4, 5 positions. Okay, what are the possible angles here? If they're all occupied, then we could have 180 degrees, right, with X at the center. We could have from here to here to here would be 90 degrees. Right? Let's see, 180, 90. What if it's on the triangle? We go from here to here to here, 120 degrees. So those are three possibilities for angles in a trigonal bipyramid. If we have one lone pair, question is, where do we put that lone pair? Here. I mean, do we stick it way up here? Or do we put it on the triangle? Yeah. And that's based upon physical evidence. Right. We're not trying to logic this one. So if we put it on the triangle, what do we got? Well, now we've got this X, and we're bonded to something here, we're bonded to something there, we're bonded to something here, and bonded to something here. And this position is occupied by a lone pair. So if we turn that on its side, what does it look like? A seesaw. So with one lone pair, we have a seesaw. With two lone pairs, right, if we take this one out, the second lone pair is also on the triangle. Now we have a T-shape. Two lone pairs is T-shape. Okay. 3 lone pairs is linear because now all 3 of them are lone pair and we go like that. Linear. Okay. 6. If we have 6 groups, go back. We have 6 groups. Now, instead of this triangle in the center, we have a square. And a square in the center with something up here and something down here is, geometrically speaking, an octahedron. Right? Hedron means surface. So it has 8 surfaces. And if you draw a triangle on one side, a triangle, 4 triangles around the top and 4 triangles around the bottom, you got 8 surfaces. So this is a tetrahedron. That. If, and what are the possible angles? Right, 90 degrees is it. Well, 90 and 180. If you go from the top one down to the bottom one, that's 180. But the rest of them are all 90 degrees. All right, if we have 1 lone pair, let's see, we change that to a square. Like this, do it like that. If we change one of them to a lone pair, where's it going to go? Well, actually, in this case, physical evidence says the lone pair goes up here. Okay. So with 1 lone pair, we have a square pyramid. You know, just like the Egyptian pyramids on the plaza of, the plateau of Giza Plateau. If we have 2 lone pairs, the other one goes down here. So now we have a square planar. Okay. I guess we'd have 3 lone pairs. Then we'd have a lone pair here. Right? Then we have that, that, and that. T-shape. Yeah, T-shape. I think. 1, 2, 3. Where would 4 lone pairs? Well, if we had 4 lone pairs, it would be bent. I can't think of an example here. Okay, so we have possibility of 180 degrees and 90 degrees for this one. We have possibility of 90, 120, and 180. And it just depends on how many atoms are in the molecules, to which ones of these you have to throw out. Okay, so those are the possibilities. Okay. We got 10 minutes. Let me see how close I am to the end. We got that one, and then we got this one. Okay, we're pretty close. This particular molecule, a phosphorus pentachloride, if it's in the solid or liquid, in the gaseous or liquid state, it's only PCl5. So that means it has five groups. It's a trigonal bipyramid. Right? But if it's in the solid, it splits. Half of them go to a PCl4 plus and half of them go to a PCl6 minus. So if we draw the geometric structures for the ions in the solid, right? Well, the trigonal bipyramid is a no-brainer, right? But how about the Cl4 plus? Count up the number of electrons. We say, all right, what are we going to have? We got a tetrahedron with a plus charge. Yeah, don't forget the plus charge. And if we go to PCl6 with a minus charge, we get an octahedron. So in the solid, you've got the tetrahedron and the octahedron somehow in that geometry. All right. The last description here is a noble gas that actually forms a compound. And I think we're using xenon and fluorine. In nature, they don't do this. Right. But if you're a graduate student and your professor says you do it, you do it. So they made a compound with xenon and fluorine. And what we want to know is what's its geometry. So if we draw the Lewis dot structure, right, and we determine the electronic configuration, we find that it's an octahedron with 2 lone pairs around the xenon. Okay, so where do those lone pairs go? They go at the apex, top and bottom. That means that what's left for the molecular geometry is square planar. Now, is that molecule polar? Well, the bonds are definitely polar because fluorine against a noble gas, it has to be polar toward the fluorine, but they're all equal in magnitude and arranged in such a way they cancel each other out. So this square planar molecule, xenon tetrafluoride, is nonpolar. That's the whole gist. Now, this slide just says, okay, what if they're on the square? Well, then you get a seesaw. But we know that it's not a seesaw. Why? Because the bonds are polar, but the molecule is not polar. And the only way you can get that is for the lone pairs to be out here and the square to have all the fluorines on it. I mean, if you do it the seesaw way, then you have an unbalanced polarity for the bonds, and the molecule should be polar, but it's not. So that's how we tell the difference. Let's see, square planar molecule. Let's see, that's it.